So I'm going to give you an update on where we are with Bioheat and our work on trying to provide the technical foundation, the technical documentation to help make the case for why B20, just at least B20, is an okay fuel and ought to be accepted formally by the national agency. So we've had to make the case, as part of this exercise, we've had to look at the entire heating system, and we've had to make the case for is Bioheat, is biodiesel and heating oil, is it safe, every aspect of it, and what are the technical problems. And one of the things that we kind of focused on as we went through this is we sort of looked for the cliff, and from a very technical perspective. Well, what's the biodiesel level at which, for legacy equipment, we're going to have a problem? Where are we going to fall off that cliff? And then once we understand where that cliff is, then we'll go back and we'll back off of that, build a technical case for this is what we ought to do. So we've kind of I guess our mission has been finding what aspect of the technology gives us that cliff. So we've looked at a lot of different things. Elastomers are really, really important, I think, in this equation. The seals that we have in legacy equipment, how much biodiesel can they handle before they fall apart? Yellow metals, there's been a lot of discussion about yellow metals, and it's even been proposed that if you're converting to a biodiesel or bioheat system at any blend level, you should convert from brass and copper to stainless steel everywhere in the system. Obviously, a major barrier to market implementation. So, but you know, we had to address it. I mean, is there anything to this technically or not? Burner performance. Of course, you know, it's critical that the burners perform acceptably, and you know, pretty much UL 296 defines what that performance criteria is: low voltage ignition, cold ignition, things like that. We also looked at tank mixing and cleaning phenomena, and then finally to document the field experience. So I'm going to give you an update on where we are kind of with all of these things. Let me start off by talking about the tank mixing and cleaning phenomena. So everybody knows that biodiesel is a solvent, and I guess it's common knowledge that if you convert from 2-oil to a biodiesel blend, that it'll dissolve suspend the sludge in the bottom of the tank, and so you'll have to do filter changes, accelerated filter changes for a while as you make that changeover. So I guess that, you know, we've heard a lot of that. We've looked at that really hard. I guess the only thing is we have not been able to prove that there's anything there. We haven't been able to find any solvency effect or increased dispersion of sludge associated with biodiesel. It's kind of a myth that continues and it goes on. It's even I'm starting to believe it, but I just can't find any proof or evidence that, in fact, that's true. Okay, so combustion, I'm just going to say a very little bit about it. John called me a flamehead before. I do like to burn things, but and we you know, we do a lot of combustion work in our lab, but what I guess we found is that that's not what's really important. We found that the biodiesel blends burn really well. We haven't seen an issue, certainly not at the B20 level. It's completely insignificant. As you go up to higher and higher levels, you know, one of the things that we have seen, we did some experiments last week with a conversion from 2-oil to B100, you know, direct two fuel streams, direct conversion, and clearly there's a change in CAD cell resistance, and we had to adjust the excess air to bring the CAD cell resistance back in range again for proper operation with the burner. That's a B100 thing. It's kind of, I guess, the only real interesting thing that I have to report about combustion and biofuels. There's a lowering in NOx, which is important. There's a lowering in particulate emissions. Particulates in residential oil burners, soot is all about the sulfur content in the fuel, unless it's operating terribly, which is a separate problem. But normally operating burner particulates are all about the sulfur content in the fuel. Biodiesel is basically a sulfur-free fuel, so conversion to biodiesel in direct proportion reduces the particulate emissions. Well documented, I think, on that. The other thing I was going to say is John mentioned the B100 burner, which was one of the things that came out of the discussions up at Brookhaven earlier this month. I was pleasantly surprised at how much interest there was in that as a NORA sort of commercialization development activity. And further, the manufacturers who were there are very interested in pushing a B100 burner. Now, I know that AMERIgreen has been an absolute pioneer in this area and has done a bit of work in this area and has demonstrated that it's possible, it's feasible to get a B100 burner listed. I mean, that is a huge accomplishment, even if the burner is not widely available on the market. I think it's really leading the way for kind of setting aside doubters who say this can't be done. It's been done. It can be done. So there's a lot of interest in that. I'm gonna skip this. This just demonstrates the Nox reduction associated with biodiesel. You know, things like this are important. Nox is not regulated in this industry. But if we go to state legislators and say that, you know, we've got this great new fuel, it increases NOx, but we don't really care about NOx, it will be a less friendly reception than if we say we've got this great new fuel that reduces NOx, by the way. So it's absolutely moving in the right direction. Okay, so elastomers. So we've done a lot of work on elastomers. The focus on elastomers has been the specific nitrile seal that's used in the most common pump in the country. It's a nitrile material. It's a hard nitrile material, and our concern was will this pump leak? At what biodiesel content level will we have technical problems with these seals? We work with the pump manufacturer. We work with an industry group of advisors, set up a test protocol. We did it in two different ways. One is we looked at the basic slabs of material, and we looked at their tensile strength, their hardness, their swell, all of the basic mechanical properties that associate with materials, and at what biodiesel level do we have problems. We also ran pumps. Manufacturers said, you got to run pumps. So we ran pumps for a year. Some 42 pumps were run. We've got more pumps running now. So basically, the test was a failure, and it was a failure in a sense that we really didn't find this cliff that I'm looking for, right? I mean, the biodiesel blend wall, if you will. So tensile strength, no difference, 0 to 100% biodiesel. This is a month exposure at about 100 degrees Fahrenheit in an oven. Impact of the fuel on tensile strength. Nothing up to B100. Hardness, another important parameter. No impact up to B100. Compression set, another important parameter. So if you squeeze it and then let go, how much does it come back up? Does it bounce back or not? Again, no impact up to B100. Swell, no impact up to B100. So in a way, we're not accomplishing what we wanted to accomplish. We're not finding a practical limit on biodiesel content based upon elastomer compatibility. Now, one thing I'd like to mention is that this is all with on-spec fuels. If the fuel quality is bad, and specifically, I mean if it has a high acid number, if it's way out of spec on acid number, it can affect the elastomers. So there's been a lot of work that's been done, a lot of field stuff, a lot of lab stuff that's been done around the world. And in a lot of that work, the quality of the feedstock fuel hasn't been documented. So, you know, was it an acidic fuel or was it not an acidic fuel? An in-spec fuel has no problem here. If you get an out-of-spec fuel, then you could have elastomer interactions that are a problem. Here's the effective acid number. This is swell. So it's all B100. On the left here is a low acid number. On the right is a high acid number. The limit for acid number is 0.5. So if you go elevated in acid number, you can get higher than a 25% swell, which is considered the limit. So stay away from low-quality fuels. We did an awful lot of looking at the seals in tremendous detail. There were a year's worth of pump tests done at Penn State, different biodiesel blend levels, again, trying to look for the blend wall. So we did a lot of really close examination of the sealing edges of these lip seals on the pump shafts to look at, you know, how much damage we're getting. So one of the things that we saw from the tests at Penn State, so this was a 5-minute on, 1-minute off for a year cycling pattern. We saw that the pump seals were getting beat up pretty good, and this happened with all fuels, B0 all the way up to B20 in that particular test. And I guess our basic conclusion was that if you cycle a pump 5 minutes on, 1 minute off for a year, it's a pretty brutal exposure of a pump. We didn't see any of this in the field, so this is a B20 blend operating 3 years in the field. We've gotten this back from a service organization. Again, the edge, the sealing edge of the lip seal looks just fine. We didn't see any damage. This is B100, 6 months operating in the field, and again, we didn't. It's a perfect looking seal edge, and I think that we're going to try to collect some more of this data. So our conclusion on seals was nothing. So yellow metals, I think what I'll do is maybe zip through this pretty quickly. Earlier this week I was at the ASTM meeting where we were discussing going to B20 blends across the board as a universally accepted fuel. This was the debate at this hundreds of people in this debate. People from the automotive industry, people from Europe, people from the oil industries. And so I had presented a lot of my data. And basically, to make a long story short, we don't see any interaction of a practical consequence between yellow metals and biodiesel. So it's another kind of myth that we're just not seeing a practical implication. It's certainly not a good idea to change to stainless steel. And we got some pushback on that. I mean, well, why not change to stainless steel? So I'm going to skip this. Basically, summer shutdown, 6 months, B20 blend versus heating oil, fuel line, nothing. We're just not seeing any interactions here. High temperatures, atomizers, brass versus stainless steel. Again, we're not seeing anything. 175 degrees F for 4 weeks, really a severe exposure. And this would be kind of what a nozzle would see after shutdown, heat soaked back from a refractory combustion chamber. You know, again, we're just not seeing anything, unless it's a low-quality fuel. If it's a low-quality fuel, and specifically if it has a high acid number, it's a different story. Then you'll start to see some issues interaction between the fuel. At least you can see something you can measure in terms of an interaction between the fuel and yellow metals. But unless I go to a high acid number and a completely out of spec fuel, I can't see anything. I think I'll skip some of this stuff. The Penn State pump testing, different biodiesel blends, 0, 12, and 20%, 7 pumps at each fuel blend, both ultra-low sulfur and 2 oil, 7,000 hours of operation. Again, this 5-minute on, 1 minute off. The metric here was seal leakage, and we work with the pump manufacturer as a very precise measure of seal leakage rates and quality, and these are very low. These are, you know, how many drops do you get? So the bottom line is that the seals leaked less. Their seal rating was better at the higher biodiesel blend levels. So both with ultra-low sulfur and with 2 oil, less seal leakage with the 20% blends than without the biodiesel in there. So our basic conclusion, I'm not going to read this, is we're not seeing adverse effects that would give us a technical blend wall for biodiesel. We did a survey and some of you may have seen these results or even participated in this survey. And this has turned out to be really useful and really, really interesting. So this is the number of Bioheat customers. So think homes or buildings is a customer that are using biodiesel at different blend levels. So up to B5 in this survey, we got 90,000 homes. But I guess maybe that's not a surprise. But if you look at all the other numbers, we had, if you look at B10 to B18 plus B20 and then even higher than that, in this survey, and we think this number is low, something like 35,000 customers or buildings or homes. So, I mean, that's a huge experience base that doesn't exist anywhere else in the world. And it's awful hard to argue with that many customers already using biodiesel at those blend levels that there's a problem with it. In this particular survey, I had 380 customers at the B80 to B100 level, and I understand that's considerably higher now, so maybe 1,000 or so is folks have already gone, well, up that high. I think overall the story is really encouraging. So when I was at the at the ASTM meeting earlier this week, one of the things that was put forward, and this is great debate, is changing the definition of number 2 oil to allow up to B20 across the board. There was a lot of resistance on that, and I don't think that that's what they want to do. I think what they want to do instead is to have a separate grade of fuel. So there'll be home heating oil, number 2, which can have up to 5%, and then a separate grade, which will be B20 blends. It's a start, and I think that's going to be, I think the next big push in the next 6 months will be to get that approved. Many of the comments and concerns that were raised will go away if that's the path forward. One of the things that we got some resistance on was our survey, and one of the things that we got in the survey was, are there any problems associated with using biodiesel? And we did get some problems that came back. There's some, nozzle fouling and sludge problems, and filters get fouled and things like that. And so I want to show a little bit of information on that stuff. So, okay, so sludge, sediment, particulates, does this occur often, sometimes, rarely, or not recorded? So sludge, 41%, sediment and particulates in fuel, 31% said often, waxing, 16.7% said often, water and pour point also occur as fuel quality problems. Rate of occurrence of these heating equipment problems: plugged nozzles, 60%, clogged filters, 50%, clogged screens, 48%. These are reporting these as problems that often occur. But the important thing about this survey is that this was done in 1990, before there was any biodiesel. And so the point that I find it's a challenge to communicate back to the folks like ASTM who are involved in this is that fuel-related service problems have long existed in the industry, and they need to avoid looking at fuel-related service problems and saying, oh, it's biodiesel problems. It's not. I mean, it's long been recognized that this is a challenge for this industry, is maintaining good operation with this quality fuel. And I think that we need to maybe put out more information that makes it clear that it's relative to a baseline, kind of defining the baseline, which we understand, but other folks maybe don't understand. We're currently involved with field sampling, where we're going out, we're taking samples from the field. We're trying to look at biodiesel content across the board, how much is there out there, and what's the quality of the blends that are actually in home tanks. We just think it's time that we start to generate a better set of data on what's actually happening out there in the field. And so if folks have sites that they would like to sort of volunteer to let us come in and do some sampling, would be interested in talking to you. Okay. Okay.
Thank you very much, both profound. And I think that conventional, wisdom is that as you introduce biodiesel, you're going to see some changes, some potential effect negatively in the existing systems. And I think it's absolutely fantastic. And obviously, it benefits our efforts, but it's fantastic to see that it's an improvement, in the existing equipment. Not just it's going to be the same, but enhancing. It's terrific to be able to see that and to recognize that not only are we getting a better marketable fuel, it's our systems are responding to it even better. I'm going to take some time to have some questions and answer with John. Yeah.
Tom, you talked about flame quality, and you had the two pictures there of the bio flame and the regular 2-oil flame.
Right.
Did you test any of those flames in cold temperatures? One of the things that we came across was that in very cold temperatures with cold fuel at B10, our ohms readings were just off the charts on the CAD cell relays, and that was pretty consistent.
Oh, all right, so you got high CAD cell resistances? So
they couldn't get a clear reading because I guess the fuel was too lean. When it was extreme cold temperatures, the technicians thought there were issues with the relays, so they would replace them, and that wasn't the case, and they realized that it had to do with the temperature of the fuel.
Yeah, so sure, it can happen. I mean, there's been, we've heard a lot about cold, low temperature problems this winter especially. And to some degree, it's a question of looking at where's the tank? Is it an outside tank versus an inside tank? Of course, is a question. But then what's the properties of the fuel? What's the cloud point of the fuel? What's the pour point of the fuel relative to the storage temperature? I think, and so if you're starting to plug filters, you're going to start to reduce fuel flow, and that can change CAD cell resistance also. In general, we find if you get it to the nozzle, it'll burn fine. So that the CAD cell won't be affected much. Where we've looked at low temperature oil, one of the things that we've done study like that in the past, where low temperature oil impact on combustion. With a one pipe system, we find that there's so much beating and heating in the pump that it's pretty hard to transfer a low temperature all the way through to the nozzle. 2-pipe system maybe more so. But yeah, so I would say know the properties of the fuel. Handling low temperature fuels, you've got to know your temperatures of your storage and then the properties of the fuel that you're dealing with.
You talked about cutting the air. You talked about with B100 having to cut the air back to affect the CAD cell resistance, and is that because there's inherent oxygen in the biodiesel?
That's exactly right. So we did some experiments last week. We have summertime. We have students in, and so we're doing a conversion from 2-oil to B100. So couldn't get it to run on B100 because the CAD cell resistance was too high. The control didn't see it. So one thing, there's different controls, right? Some look for a 5,000 ohm, some look for a 3,000 ohm, and so. This one looked for 3,000 ohm, and it wasn't getting that low. When we checked the O2 level firing 2-oil, it was too high anyway. So we were but nonetheless, it ran fine on 2-oil with high O2, but it wouldn't run with biodiesel. And you're right, the O2 is higher because of the inherent oxygen in the fuel. So I don't see this as something that's a major concern. If you convert from B0 to B100, you may need to trim the excess air back a bit to be sure that your CAD cell resistance is in range. Sure, Dave.
One of the things we discussed out there at Brookhaven early this month, Tom, was the timing, I think it was, for a PON, and I think you were talking about September. And could you just tell the audience what a PON is and how that relates to the whole process?
Sure, no problem, that's easy.
Okay. PON is a public opportunity notice. So what Nora, for our research agenda, that was step one, was what I described. And so what we will do from that is we're wrapping that up into a little book We'll distribute that to our board of directors and our, jurisdictional committees, and they will basically say that's where we want to be going. And we'll put that out and kind of a notice to everybody, speaking from the highest mountaintop. If you have ideas how to accomplish things on our agenda, please submit them and basically bid to do work for us. That will then be evaluated by our research committee and then our board of directors, and then we'll fund projects that we think are most beneficial for the industry and get us the best prices.
Dr. Butcher, question for you. A couple of questions. Just a moment ago, you were talking about the excess O2
Right.
at B100. Do you find that as you drop down in the blend, that disappears, that issue?
Yeah, it's pretty much directly proportional to how much biodiesel you
Okay,
have
so
in the blend.
at B20, for example, it doesn't become an issue?
At B20, it's not an issue. So if you were to develop a B100 burner, which was one of the items on the list, and I think folks are kicking us around, trying to seriously commercialize this, can you use the current CAD cell system? This is the debate, not my opinion. Do you need to go to a flicker sensor, or maybe a larger CAD cell that takes in more light, or maybe change the limit setting? I mean, we pick 3,000 or 5,000 ohms as the point at which a flame is proven. Why is that? Why can't we go to 7,000 ohms? I mean, is there, So there's some of that discussion. Again, my experience has been, a little careful tuning, you're fine with an existing system. But I think that the debate is, well, for a more robust system going forward, should we change sensors or do something else?
But this is only at the ultra-high blend levels.
This is at the ultra-high blend levels, right?
And the other question, you showed, you were talking about the yellow metals.
Right.
And no deterioration after 6 months.
Right.
You confident that if it didn't happen after 6 months, it's probably not going to happen?
I am. Part of what we did is, we took equipment from the field. We took nozzles from the field and pumps from the field, and we're not seeing anything. So these are units that have been running for years out there in the field, and we're just not seeing anything there. It gets a little frustrating because if you store a sample of biodiesel at elevated temperature with a copper coil in it, you can show that copper coil will have a higher let's say 120 degrees F for a year. When you have a copper coil in it, you'll have more degradation than when you don't have a copper coil in it. And so folks say, aha, there's a copper effect. There is a copper effect, no doubt. But does that mean anything practically? I mean, we don't normally store oil at 120 degrees for a year, right? So, at the highest temperature point we see is the nozzle. And the fuel that's exposed to the nozzle, especially for that high temperature point after shutdown, the heat soaked back from the combustion chamber, that fuel goes away and the next batch comes through. And so, it's not the same oil that's stored over and over again. I just can't see it. No.
I have two questions. I think one for Tom, maybe one for John. For Tom, have you guys done any FGR, EGR experimentation, flue gas recirculation for low NOx or blue flame type of tests?
What a cool question this is. We have. So not so much in connection with biodiesel, Gary, but in general. And yeah, especially, what we kind of looked at is starting a burner and then after it's up and running, then introducing the exhaust gas recirculation. And you can have a tremendous effect on NOx. You can very definitely reduce NOx, and with a conventional burner, conventional retention head, spray atomized burner, no need for a blue flame tube, you can get to a blue flame and get good results. One of the things that, and we have, we've done a lot of work on NOx, but we just find that there isn't a lot of interest in reducing NOx. It's just, not a subject that grabs a lot of attention. There are no regulations on the residential scale. In Europe, of course, it's a completely different situation. But we just haven't found that, that there's a lot of interest. It's a very fun subject, though.
And it's also an easy way for to make the CAD cell not work either.
Oh, absolutely. Yeah, no, forget the CAD cell. It'll, I mean, because, you know, once you make it lighter, we do that exhaust gas recirculation, the flame gets lighter and lighter, and then, yeah, no, you have to go to a different control.
Second question I have, and I didn't mean to hog the mic here, but for John, one of the things that I see, this on the NORA side, is that you have a lot of technology opportunities out there, and one of the things to make a technology work is that it requires somebody, a manufacturer, to invest in it. And to pay for the tests and the research and R&D is one thing, but also the more important thing for all of us is to make sure that these products and these technologies come to fruition, they come to market. So in the scope of the NORA funding, I know that there's been an attempt to skew funding towards the R&D side specifically. How much of that is going to be targeted towards actual manufacture and getting products to market?
That hasn't been decided, you know, just because we haven't seen what the manufacturers are willing to do. But I think that, you know, I'll say our operating culture has been very much oriented towards trying to get products in field. You know, that whether it's a Peerless or a Thermopride or a Beckett, you know, before they put any engineering time into any subject, they want to see that it has a market. You know, even though, you know, let's say the project's going to cost $300,000 and they're going to put in $75,000 of in-kind on it, and we're going to do $225,000. They still don't want to do it unless they think they're actually going to get a product. I mean, none of our people are, you know, just research for hire companies. So I think we will continue that model of trying to get products that they see as a product that this industry might want to buy and use in the future. So we will try to continue that and work closely with them.
For Tom, I know you've done a lot of work with Fulton boilers in the past regarding condensing boilers and so on. And as far as I could tell, there hasn't been anything that's come out that they've produced or any other manufacturer that is anything other than that commercial scale. Have you seen any you know, Fulton in particular getting closer to producing like a residential size condensing boiler? And the second part of the question, is truly the sulfur content the only barrier towards condensing boilers, for oil-fired condensing boilers being more prevalent in the market?
Darren, great question. So Fulton is a commercial boiler manufacturer. They're not in the residential market at all. So that it's just not what they do. Now, so I have not seen them moving in the residential direction. But you know, you're thanks for raising that. They did, and we work with them jointly on a project. They did commercialize a 2 to 4 million BTU an hour dual fuel boiler, gas, liquid fuel, listed for B100. So that's on the market. I know, I haven't talked to them where they're at in several years on that. I know they had installed one in Chicago, of all places. So yeah, so it's really commercially available. I think it's a Riello burner, big. I mean, this is big stuff. So, you know, I think that's going. I'm sorry. And your second question was, oh, is sulfur the limit? Yeah. So with liquid fuels, you can get to an efficiency of about 92% without condensing if you push it hard. So there's one you know, argument out there that says, go as high as you can without condensing and don't deal with the trouble associated with condensing. With condensing in a boiler, you can go 95%. Of course, it all depends on the return water temperature. And in a furnace, warm air furnace, you can go to 98% because you've got that 70-degree cold air coming back. Sulfur is absolutely the limit. The higher the sulfur content, the higher the corrosion rates are going to be, the higher the scaling is going to be in both the near condensing and the full condensing range. and folks will often compare gas condensing to oil condensing and say, well, oil's a lot harder because of the sulfur. The other factor that comes into play, though, is the exhaust gas from gas has a lot higher water content to it. It's just, and so it condenses easier and condenses more strongly for a given set of return conditions. With oil, you've got less water vapor in the exhaust, and so that's why you can go as high as 92%. You can't do that with gas without condensing. So the condensation rates tend to be lower in an oil system than they are in a gas system. So the condensate tends to be more concentrated in an oil system, even at the same sulfur level. And so it's still a little bit harder with liquid fuels than it is with natural gas, just because of that difference in the water level. But I guess probably the simple answer to your question is, yeah, it's pretty much all about sulfur.